Welcome to Part 6 in the module on an overview of pattern relationships. In the previous parts, we've motivated why we need pattern relationships that go above and beyond pattern collections, talked about some of the various kinds of relationships, given an example from the domain of avionics control systems to illustrate some of the key patterns for concurrency and network systems. We've talked about pattern relationships like pattern complements, pattern compounds, pattern sequences. And in the previous part, we gave an overview of pattern languages and talked through some of the ways in which they allowed us to be able to navigate through the design space of developing some communication middleware. In this part of the module, we're going to go and have a little bit more detailed analysis of a particular piece of some of those patterns in the pattern language. Just to recap our pattern language thus far, our pattern language for the broker is composed of about 9 other patterns, not comprehensive, just some of the key patterns you'd run into if you were developing a broker that had to be flexible, had to be efficient, maybe have to be scalable, and so on. And we talked earlier in the previous part about how you can navigate through the different paths in this pattern language to meet your different requirements under different circumstances. It's also important to realize that while I'm presenting this particular pattern language in the context of brokers, we'll also come back later in other parts of the course and see how many of the patterns in this particular pattern language can be applied for other kinds of concurrent and network software above and beyond brokers. So it's a worthwhile pattern language to know for almost anything you'll do in the concurrent and network space. The particular sets of things we're about to talk about in this part of the module is to show how our pattern language can be used to compare and contrast several alternative mechanisms for broker concurrency. The reactive approach, using the reactor pattern, which is very simple. A more scalable approach, using the HalfSync, HalfSync pattern. And a more predictable approach, using the leader-followers pattern. So let's take a look and see how these different approaches can be applied in a real example. So if you were building a broker the traditional way, then invariably you'd have to worry about some low-level communication mechanisms. You'd have to worry about something relating to connection management. You'd have to worry about something relating to event demultiplexing. You'd have to be worried about some kind of protocol that's used to send information between different parts of the system. Imagine, for example, we're using our avionics control system as the motivating example. We've got different processor boards, and they have to be able to communicate. Different parts of the application have to talk back and forth between different parts of the application split across the processor boards. The problem we have is people often historically have tightly coupled the connection management, demultiplexing, and protocol processing. Here's a simple code snippet that illustrates a very common problem. People will often hard code the use of particular event demultiplexing mechanisms, things like select or poll or dev poll or wait for multiple objects. They may also use specifics of particular platform-centric communication mechanisms, such as sockets for Unix, which will break if you move to different platforms where you want to use different mechanisms. Likewise, there's a tendency when you're programming with sockets and select to write loops that go through in a linear fashion the set of handles that may have something ready on them in order to figure out whether they've actually got anything to work on. And this linear search can become prohibitively expensive if you have lots of things that you're trying to keep track of in your solution, in your implementation of the broker. So what's a solution we can apply? Well, one way to solve this problem, to keep things simple, is to apply the reactor pattern in order to be able to decouple the generic event demultiplexing and connection management behavior from the protocol code that the broker provides to communicate across the various processor boards or address spaces. The reactor pattern is a POSA 2 pattern that's used to structure event-driven software so it cleanly separates the demultiplexing and dispatching code coming from a multiplicity of sources, multiplicity of clients, multiplicity of event sources, and so on, from the behavior and processing that's done once the events have been demultiplexed and dispatched. So typically you have some kind of event loop, and you wait for something to happen down in a synchronous event demultiplexer, and when that something happens, then the reactor will dispatch various hook methods that are implemented by subclassing from an event handler interface. You can take a look at the POSA 2 book for more information on Reactor, or take a look at this URL for an earlier version of a paper describing it. Here's a picture that illustrates some of the dynamics in the reactor pattern. As you can see here, there's an initialization phase where you register various handlers, things like acceptors or service handlers, with the reactor, and then you turn over the flow of control from the application and the initialization phase to the reactor framework, and from that point onwards, the processing is typically driven by callbacks. Here's an example of how we could apply the reactor pattern together with its common friend, the acceptor-connector pattern, in the context of a very simple implementation of a broker. We would have the broker using a reactor to wait on some set of endpoints, things like sockets or other forms of inter-process communication handles. And when something happens on those handles, on one or more of those handles from different sources of events corresponding to different client requests, then the reactor will return and invoke callback hook methods through other parts of the infrastructure to accept connections, read data from clients, and pass them up to higher level parts of the middleware, the broker middleware. One of the nice things about using the reactor is it provides a very simple, coarse-grained concurrency control mechanism, where there's only one thread of control taking place at a time in the broker, and therefore you don't have to worry about locking and deadlock and other forms of race conditions and scheduling hazards to worry about. But there are some problems with this simplicity. For example, if you were to try to run your implementation on a multi-core platform, you'd find that there was only one thread of control, and so only one thing at a time could be dispatched by the broker, which would potentially wildly underutilize the amount of processing that you might have at your disposal. Likewise, if the event handlers that are called back take a while to run, or incur a page fault, or other kinds of blocking I/O operations, or run into flow control conditions, that could very well end up starving out other clients from being processed. So we can have a situation where we're either not taking full advantage of the hardware, or we're starving things out because we only have one thing going on at the time. So how can we address this? Well, instead of using the reactor by itself and having coarse-grained concurrency control for the whole architecture, instead we could apply the half-sync, half-async pattern to scalably process requests concurrently in different threads of control. The half-sync, half-async pattern is another POSA 2 pattern, which you can read about at this link, and it splits up the architecture of some part of the software into multiple layers. There's the so-called async layer, or reactive layer, where you can do things like run a reactor or some kind of interrupt-driven callback mechanism if you're programming inside an operating system kernel, for example. And when low-level events occur, that async layer does just enough work to read the event from the source of events, put it into some kind of message, and then stick it onto a request queue that sits between the async layer and the sync layer. In the sync layer, there can be a pool of threads, or even processes in some situations, that wait in so-called hungry puppy fashion for the next piece of work to come along, the next request. And when a request comes along, one of the threads wakes up, reads that request, and processes it. The nice thing about this particular approach is now we can have multiple things taking place at the same time. This particular dynamic view of the half-sync, half-async pattern illustrates the flow of control a little bit more clearly. The async layer is driven by either event dispatches or callbacks from interrupts or signals. It takes the data, does a little processing, puts it on a queue, and then that wakes up one or more of the threads waiting that are blocked in the sync layer, because they can block in the sync layer. They can't block in the async layer. They can block in the sync layer. They can wake up. They can read the request and process that. And you can dictate how much concurrency is used by the number of threads that you spawn that wait in the sync layer. So here's an example of how we can apply the half-sync, half-async pattern to our broker. What we can do here is we can have a pool of threads that are running in the upper layer parts of the middleware in something called the portable object adapter and its thread pools. And we can still have a single thread down in the lower level parts, in the reactive part, in the orb core part. And when a request comes in from a source of events like sockets, then that request is taken out by the reactive layer, converted to a message, inserted into a queue or potentially a set of queues, depending on how you want to organize the threading and the queuing. And then that queue or queues can then be serviced by the threads running in the sync part of the half-sync, half-async design. The nice thing about this particular approach is it allows us to be able to have multiple requests running at the same time without having to worry about interfering with each other. And as long as your underlying operating system supports preemptive multi-threading, then these threads can block without interrupting others, without having problems and starving other applications out. But there are some problems with half-sync, half-async. This is particularly an issue if you have lots of very short-running operations. And the reason we have some problems is that splitting things up into layers with threads in each layer adds some extra sources of overhead. For example, the thread that reads the data in the reactive layer is not the same thread that processes it in the sync layer above. So as a result, we're going to probably have to use dynamic memory allocation, which incurs fragmentation and overhead, and also requires some kind of synchronizer or mutual exclusion or mutex lock to serialize access to the heap, to the free store that we use to allocate the memory and deallocate it dynamically. Likewise, when we move things between threads through our synchronized request queue, we're going to have to acquire and release locks, and there's some amount of overhead associated with that. Likewise, if we move things between threads, we're most likely to incur some kind of context switch or mode switch. And this also will chew up many hundreds or thousands of low-level operating system instructions when we move things across the threads. Yet one more problem we have is if we're running on a multi-core or multi-processor machine, then chances are moving data between threads or between cores will require some kind of cache management or cache validation and invalidation protocols to be run at the hardware level, which also may incur some additional overhead. Now, if our requests take a long time to run, not a big deal. These operations won't cost much. In contrast, if these tests and these operations take a long time to, or a short time to run, then this overhead may become prohibitively expensive, and we might prefer to do something else. Well, what's that something else? As it turns out, that something else could be to apply the leader-followers pattern. This pattern helps us to enhance predictability and efficiency with some cost or some loss of scalability, as we'll talk about. And under the right circumstances, it could very well be the right pattern to choose to meet your needs. This particular pattern is also described in the POSA 2 book, and you can read about it at this paper URL. The main idea for the leader-followers pattern is to organize the pool of threads in such a way that it reduces thread overhead and jitter, jitter being variation in latency. And it does this by allocating the pool of threads and then having one thread at a time, the so-called leader thread, wait on the event demultiplexer, such as some kind of specialized reactor, while the other threads block on some kind of condition variable or semaphore or some other synchronizer, waiting as followers. So whenever some work comes in to be done, the leader thread will wake up, read in the work to do, and it can read it into the thread stack, which means there's often no need to allocate memory dynamically. And then that thread morphs from being a leader and becomes a processor thread. It goes off and does its thing. Before it starts to do its thing, it elects one of the followers to become the new leader, so it can go back waiting for the next thing to do. And that leader thread then goes off, becomes a processor thread, does its processing, and when it's all done, it returns back and becomes a follower again if there's no other, if it's not able to become the leader right away. And so by doing this, you incur less memory management overhead. You don't always have to allocate memory dynamically. You reduce the number of context switches. You simplify synchronization. And you often are able to avoid having to move the data between the different cores or CPUs because things have better locality of reference or affinity for a particular processing element to do its work. A good analogy, by the way, for leader followers is the way that most airport taxi stands are organized. If you go to an airport to get a taxi, you'll often find a queue of taxis and a queue of people. And the way in which the people in the taxis self-organize is very much like the leader-followers pattern. The typical rule is that the first taxi in line is the leader, the rest are the followers. The first person in line is the one that gets to get in the leader cab and be driven to their destination. In other words, the cab moves from being a leader to being a processor or a delivery cab. The next cab in line becomes the next leader, the rest remain followers. The next person in the line gets in that cab, and so on. The main difference in which the cab analogy differs from the leader-followers use in a computer system is that cab drivers would typically get in fistfights if a processor driver went back and cut in line and became the new leader. They typically want you to go to the end of the line to wait your turn. In contrast, computer threads don't really care about who gets to go next. So it's often the case that in a leader-followers implementation, the one that's going to be the new, one is finishing up being a processor, will go back to being the leader. And the reason for doing that has to do with something called processor or thread affinity. You want to be able to emphasize giving preference to threads that have finished running recently because chances are they'll have instructions and data in their caches that may allow the system to run faster. Here's a diagram that illustrates how these interactions take place. It basically mirrors what I just described from the taxi cab example. So I encourage you to take a look at the paper to find out more about this pattern. Here's how we could apply the pattern in our avionics mission computing system for avionics control. We could have a special kind of reactor, a thread pool reactor, where you can take turns with a pool of threads going down and calling into the underlying synchronous event demultiplexer to do the work, to get the next data. And when the data arrives, that would have been taken out and then could be used to do the rest of the dispatching of that particular request to the upper layer parts of the orb. In the meantime, one of the follower threads could become the new leader and wait for the next unit of work to do. So the nice thing about this is it allows us to be able to eliminate the overhead of the separate reactor thread and synchronized request queue, so we don't have the overhead we talked about before in terms of dynamic memory allocation, synchronization, context switching, data movement between processor caches, and cache invalidation and cache management, and so on. Now, it turns out, even though leader followers is more predictable and usually has lower overhead, there still could be circumstances where you would prefer to use the HalfSync half-async design. And that's because HalfSync half-async is more scalable. One of the things you can do with that also, with HalfSync half-async, is you can rearrange the order in which requests are queued so that the order in which they're processed is not necessarily the order in which they arrive, which allows you to prioritize requests, which can be important for certain kinds of operations. So once again, it's not about one pattern being better than the other. It's about knowing when to choose the right pattern for the right job by navigating through the alternative design space. We'll now go ahead and summarize this part of the module. Pattern languages provide an integrated group of related patterns that allow larger scale reuse of software architecture and design. More than you can get with pattern sequences, pattern complements, pattern compounds, and certainly more than you can get with isolated patterns, pattern islands, and of course, much more than you can get by having no patterns at all, where you have to reinvent, rediscover all the core concepts, core abstractions each time you build software. That's clearly undesirable. One of the most important things that patterns allow us to do is to navigate through different parts of the design space. For example, we took a look in our discussions of our communication middleware broker pattern language, where we could have simplicity, just a few patterns to be able to give us a coarse-grained, single thread of control model. We also talked about how we could use the HalfSync, HalfSane pattern in order to be able to enhance scalability and flexibility. And then we also talked about how we could apply other patterns like leader-followers instead of HalfSync, HalfSync in order to be able to emphasize predictability and flexibility. As usual, it's up to the architects to figure out what the right choices are going to be, and patterns help them do a more effective job at determining what the trade-offs are and navigating through those alternatives in a systematic way. Over the years, more and more people have begun to document their experience and their knowledge of software in the form of pattern languages. For example, the POSA 4 book that I wrote in conjunction with my colleagues Frank Bushman and Kevlin Henney grouped together 114 patterns in 13 different topic areas, things like distribution infrastructure, concurrency, synchronization, event handling, component partitioning, and so on and so forth. And you can learn many of the things we've been discussing here in much greater detail at much broader scope by taking a look at the more comprehensive pattern language in the POSA 4 book. The POSA 5 book provides a much more detailed discussion of the different relationships we've talked about in the form of patterns. Pattern complements, pattern compounds, pattern sequences, pattern languages, and so on. And has many, many examples, other illustrations, case studies, and so on to help you understand these concepts and how they relate to each other. So it turns out that developing and learning patterns is not always easy. It's especially hard to write them, often much easier to learn them. But the great news is that they help to express the most powerful and elegant relationships among patterns, help software developers and teams be more productive, be more communicative, be able to produce software that will meet the needs of their customers and users in more effective ways.